This video covers problem count number of smaller elements after solve. What it means is that if we have array of nums which is not sorted, for example like this, 4 6 1 7 0 2 1, what we want to do is to provide the counts which will be array of the same size, where for each position we will count how many elements to the right from the current element are smaller than the current element. So for example, in this case, obviously there are no elements after 1, so 0. There is one element which is smaller than 2, 1. There is a 0 element smaller than 0 after 0, so we put 0 here. There are 1, 2, 3 elements smaller than 7, so you put 3. There is only one element smaller than 1, which is 0. We put 1. So 6. 1, 2, 3, 4. There are 4 elements then smaller than 6. We put 4. And for the 4 again, so 1, 2, 3, 4. 4 elements smaller than 0. So this is expected result. The count number of smaller elements after solve is similar to the count number of smaller elements before solve for the flipped array. So for visualization, it will be simpler visualize it with the kind of flipped situation, and then we can change it back to fit the requirement of this problem. So let's imagine the array, but more on 2D plane. So let's have 0, 1, 2, 3, 4, 5, 6, 7, and let's put these numbers there. So, but from backward, so it's will be 1. Let's put it like that: 1, 2, 0, 7, 1, 6, 4, right? Right. So, and then visualize it like that: 7, 1, 6, and 4. Okay, now let's iterate through these elements, and every time put those elements in the correct order. So for 1, let's just imagine this kind of slope. So 1, we put, this will be 0, this will be 7, 2, 3, 4, 5, 6, 7. So 1 we put somewhere here, and we count how many elements are already in the plane, in this kind of line before that element. So we take the first element, we locate its right position, its correct position here on the plane. So let's write it down. So first take kind of east element and locate correct position on the kind of line. So, and then after we found the correct position, calculate how many elements are before this element. So in this case, like get number of elements before before, you know, like found position position in 1. Okay, so let's take the second. Second will be right here, and we see there is already one element before that. So we can actually note it down. So let's do this. So for the first element, 1, right? Position actually 0. Position 0. We take the 1 and we put it on some kind of let's call it BST, for instance. So, and we put it in BST. So BST is empty, so we don't, you know, like we put it there, and then we calculate how many elements are kind of before it. So let's look at this BST like that. So I put 1 here, found that there is actually 0 elements right here. So I put 1 here, same representation, and there is 0 elements here. Okay, that's good. So we take second element, index IDX. We take second element. We find correct position in this array BST, and correct position, let's say here. And from that we can see that there is already one element in here. So we here before that there was, let's properly mark it, 0. So this second step is index 1. There is 1 already. Plus we found a new position for this guy, and we put how many elements before 2? Only 1 element, so we put 1. Okay, so second index 0, right? So BST at that point is 1, 2. So now we need to find the position for 0. So we look through this kind of thing right now, and we put 0 right here. How many elements before 0? Not 0, so we put 0. Okay, now let's take a look at 7. So 7, it's located right there. 7 is here. So we put 7 somewhere again, so at the end it's BST array. Up, not here. 1, 2, and 7. Okay, and how many elements we have before it? We have 3 elements. Put 3. Then at that point we have already this established the structure, and now we look for 1. So we look for 1, and the task here is to find the smaller elements. That's why what we do, we kind of put this kind of 2 elements together, right, and look everything that is lower than them right here. So this is like intuition, and in this particular case the right position is somewhere here. So for simplicity, what we will do, we put it right before this the same element, right before here, and from that we calculate how many elements to the left from it. This is 1, right? Okay, same same operation for 6. So at that point our BST looks like this, 2, 7. The new guy will go right before 7, And from that we calculate how many elements we have before 6. 4. The same approach we take for 4. BST is equal to 0, 1, 1, 2, 6, 7. Find right position somewhere here for 4 and calculate how many numbers are before 4. It's 4 again. Okay, so this is a little bit intuition what's happening. How to optimize that? First of all, obviously we want to optimize the search of the correct position, and there are kind of several approaches how to do that. Some algorithms kind of sort first, then kind of pop remaining elements to it, like in opposite direction. In this particular implementation of the algorithm, what we have is, instead of allocating the space before, you just can keep a BST as a current list. So initially it will be empty, and as we go we add more elements at the correct position, like 1, 2, yeah, BST 0, 1, 2, etc. So we just keep adding the new elements. So when we add the elements at the right position, the location of the new element, right position, by right position I mean it doesn't change the order, so elements are ordered, sorted. The location of the new element will be O log n. So we traverse the all elements, which is O n operation, and we locate the position of the kind of insertion position in O log n, and we get number of elements in constant time, right? Because this is essentially a position of the new element, so it will be all constant, right? So all in all, this seems like algorithm is O log n. However, if you look at the particular kind of details, every time we insert, we have to do this kind of operation. So depending on the implementation of the array, this actually is O n operation. So it might be costly, right? So all in all, depending on the implementation, is gonna be O n squared. However, unless there is very sophisticated, like interesting context-aware structure for inserting the elements in a log n, we kind of end up with this kind of situation. So probably here, like the more optimal, which will kind of reduce this guy, might be orbit tree or anything similar that allows to get element like search in the collection and update the collection in log n time. However, for kind of like showcase and simplicity, this is probably kind of good enough for the interview or for LeetCode to get to the most one of the best results out there. Okay, so this like in the algorithm itself, there are a couple of safety checks. First of all, like if initial array is empty, we return empty result. If array has only one element, so obviously 0, then what we do, we allocate a resulting collection, and we start traverse from the end. So this is idea when I told about the flipping part. So instead of kind of trying to get how many smaller elements are before the current element, we go from the backwards, and in this case basically we will have a symmetric kind of representation in some way. Right, so also this guy uses the function bisect left, which is nothing else but location of the proper index to insert the target element with preservation of the order, sorted order. The left part is here because for the reason which I shown at the fourth step. So when we find the several consecutive equal elements, we don't want to count them. So we don't, take the right foremost element. We take left foremost element and calculate the get the number of elements before that. Otherwise, it would return incorrect result.